Hello everyone, my name is Maciej Korczynski from Grenoble Alpes University, and the title of my presentation is Don't Forget to Lock the Front Door, Inferring the Deployment of Source Address Validation of Inbound Traffic. This work is in collaboration with my colleagues from Grenoble Alpes University, Yevheniya Nosyk, Marcin Skwarek, Baptiste Jonglez, Andrzej Duda, and our colleague Qasim from Delft University of Technology. So let's start with the definition of IP spoofing. IP spoofing refers to modifying a source IP address of a packet to a different IP address. Why spoof packets? It results in the anonymity of the sender and prevents the packet from being traced to its origin. This has been leveraged to launch reflection and amplification denial of service attacks. Just to mention, an attack against GitHub resulted in traffic of 1.35 terabits per second, where attackers redirected memcache responses by spoofing their source addresses. So this work concerns the problem of the absence of the source address validation, known also as BCP38. The standard was proposed 20 years ago in RFC 2827 as a result of a growing number of denial of service attacks. The RFC defined the notion of ingress filtering, dropping any packets with spoofed source IP addresses which do not reside within a range of legitimately advertised prefixes. This operation is the most effective when applied at the network edge. What is important? Packet filtering can be applied in two directions. Outbound filtering drops spoofed IP packets coming from the inside the customer network to the outside, and inbound filtering that filters packets coming from the outside to the customer network. Attackers benefit from the absence of outbound source address validation to launch DDoS attacks. Malicious actors make use of public services vulnerable to amplification, such as NTP servers. Compromised hosts send requests on behalf of their victims by spoofing their source IP addresses. The victim is then overloaded with the traffic coming from the services rather than from the compromised hosts, such as IoT devices. In this scenario, the origin of the attack is not traceable. As countermeasure, as described in RFC 2827, all providers of Internet connectivity should implement filtering to prohibit attackers from using spoofed source IP addresses. Now, what about filtering incoming packets by their IP source address? Pretending to be an internal host may reveal information about the inner network structure, such as the presence of closed DNS resolvers that perform DNS resolutions only on behalf of the clients located within the same network. Attackers can further exploit the closed resolvers by pretending to be an internal host and by sending DNS requests from compromised hosts to a closed resolver. That can trigger closed DNS resolvers to perform a large number of requests and, for example, overload the local victim with DNS responses. Again, an effective countermeasure for IP spoofing is source address validation, this time for inbound traffic deployed at the network edge. A number of methods were proposed to infer deployment of source address validation, in particular for outbound traffic. The Spoofer project deploys a client-server infrastructure, mainly based on volunteers, that run the client software from inside the network. The server inspects received packets and analyzes whether spoofing is allowed and to which extent. A more practical approach is to perform such measurements remotely. Jared Mock proposed a method that we refer to as forwarder-based that leverages the misconfigurations of forwarding resolvers. A misbehaving resolver forwards external clients' requests without changing the packet source address to another recursive resolver located outside its network, revealing the absence of outbound source address validation. The method based on trace route loops leverages a routing misconfiguration, while techniques based on passive detection analyze passively inter-domain traffic exchange to infer the deployment of source address validation. So what are our contributions? So we are the first to propose a method to detect the absence and presence of inbound source address validation that is remote and does not rely on existing misconfigurations or volunteers. Instead, we use local DNS resolvers, both open and closed, to infer the absence of packet filtering and the presence of source address validation either at transit networks or at the edge. So first I will discuss the proposed methodology, the ethical considerations, the results of our scans. Then I will discuss the policies of outbound versus inbound source address validation, the limitations of the proposed method, and I will conclude my talk. So we have developed an efficient scanner that sends DNS A request packets. We run the scanner on a machine inside the network that does not deploy outbound source address validation, so that we can send packets with spoofed IP addresses. We also set up a DNS server authoritative for the dracardns.com domain that captures the traffic related to our scans. To prevent caching and to be able to identify the true originator of queries in case of forwarding, we query a unique subdomain every time. It is composed of a random string, the hex-encoded IP address of the destination of our query, the scan ID, and the dracardns.com domain itself. So the figure shows the scanning setup for the 8.9.10/24 network. In step 1, the scanner sends one spoofed packet to each host of this network, so 254 destinations in total. The spoofed source IP address is always the next one after the destination. When the spoofed DNS packet arrives at the destination network edge, and therefore it has not been filtered anywhere in transit, there are at least two possible cases. The packet filtering is in place and detects that such packet cannot arrive from the outside because the address block is allocated inside the network, so the filter will drop the packet. There's no packet filtering, this is the second option, and nothing prevents the packet from entering the network. If the packet destination 8.9.10.2 is the address of the local resolver, it receives a DNS A request from what seems to be another host on the same network and performs query resolution. If the destination is not the local resolver, it will drop the packet. However, the scanner will eventually reach all the hosts on that network and a local DNS resolver if there is one. So in the next steps, the non-forwarding resolver performs the resolution by iteratively querying the root and TLD name server until it reaches, in step number 5, our authoritative server that reveals the lack of inbound source address validation for a tested network. Finally, in step 6, the DNS A response is sent to the spoofed source. So we scan the entire IPv4 address space, yet taking into account only globally routable and allocated address ranges. What is very important, we also send non-spoofed queries just after the spoofed one to the same host. So if we receive a request on our authoritative name server, it means that we reached an open resolver. Now, if this open resolver did not resolve a spoofed query, we infer the presence of inbound source address validation either in transit or at the tested network edge. Regarding ethical considerations, we send two DNS A requests, spoofed and non-spoofed, to every tested host. We randomize input list for our scanner and spread scanning activities over 10 days. We set up a homepage for the study on dracardns.com and queried subdomains. We received 9 requests from operators and excluded 30 million IP addresses for further scans and analysis. We do not publicly reveal the source address validation policies. Results for individual networks can be found on closeresolver.com. And finally, we plan a notification campaign through intermediaries, example CSERTs, and direct emails to network operators. So we performed our scan in December 2019. There were 2 scans, spoofing scan and open resolver scan at the same time. During the spoofing scan, we observed 14 million A requests on our authoritative name server, but DNS resolvers tend to issue repetitive queries due to proactive caching or premature querying. So we keep unique tuples of the IP address of the resolver and the domain name, which results in 9.5 million unique requests. So we reveal almost 1 million vulnerable to spoofing /24 IPv4 networks, almost 200,000 vulnerable to spoofing longest BGP matching prefixes, and more than 32,000 vulnerable to spoofing ASs. While based on the number of received queries, we cannot by any means conclude on the filtering policies of the entire AS, they still reveal source address validation compliance for part of it. And finally, our open resolver scan identified 4 million open resolvers. We compared the results of the spoofing and open resolver scan to reveal the absence and the presence of inbound source address validation. For every detected open resolver, we check whether this particular resolver resolved a spoofed query. If it did not, we assume that this resolver is inside a network performing inbound source address validation. Significantly more networks do not deploy inbound source address validation than deploy it. However, we note that due to possible packet losses and potentially different filtering policies, we may obtain contradictory results for ASs or even /24 networks. We define ASs and networks as inconsistent if we have at least 2 measurements with a different outcome. So interestingly enough, after our initial scan, we realized that one of our 3 upstream providers performed source address validation of outbound traffic. This means that all our packets with spoofed source IP addresses routed by this provider were dropped, while those routed by other 2 upstream providers were forwarded. By disabling this provider before the main scan, the number of inconsistent results decreased more than 2-fold. So we further investigated reasons for inconsistent results. We find that smaller ASs are less likely to perform source address validation filtering. larger ASs are often inconsistent and are more likely to pair with other ASs. We find that inconsistent ASs maintain relationships with 29 other ASs on average, while vulnerable to spoofing ASs connect to around 7 ASs on average. We also investigated packet losses, and after rescanning a sample of 1000/24 inconsistent networks, approximately 50% of them became consistent and all vulnerable to spoofing. The results obtained by running our scans and using the data of the spoofer project let us evaluate the filtering policies in both directions, inbound and outbound. To make the datasets comparable, we find the intersection between the networks covered by inbound filtering scans and all networks tested with the spoofer client. In the resulting set of 559/24 networks, we found 95 networks with no filtering in any direction, 151 networks deploying both inbound and outbound source address validation, almost 300 networks with filtering for outbound traffic only, and 15 with inbound source address only. So the results show that inbound filtering is less deployed than outbound filtering. So the results might be surprising at first glance. Why? Because implementing source address validation for outbound traffic benefits other networks and not the network of the deployment. On the other hand, performing inbound source address validation protects networks from external threats, which might be beneficial from the economic perspective. Yet, we observe significantly more networks deploying outbound filtering, and there are a few possible explanations for that. So the first one is that there is a big pressure on deploying outbound source address validation because of DDoS attacks. Second, regarding the spoofer project, those that are not aware of the issue or do not deploy source address validation are less likely to run the spoofer client on their networks. Finally, while within our close resolver project we plan notifications, the spoofer project actively notifies operators of networks vulnerable to outbound spoofing. So our approach has certain limitations that may impact the accuracy of the obtained results. We rely on the main assumption, the presence of an open or closed DNS resolver or a proxy in a tested network. If there is no resolver, we cannot conclude on the filtering policies. If the probe resolver is closed, our method may only confirm that a particular network does not perform source address validation for inbound traffic or at least some part of its address space. Only the presence of an open DNS resolver may reveal the presence of source address validation, assuming that the transit networks do not deploy source address validation. So the scanner sending spoofed packets should itself be located in the network not performing source address validation for outgoing traffic. Still, even if a spoofed query leaves our network, it may be filtered by some transit networks and never reaches the test destination. That is why we're going to test our method from different vantage points. And finally, packet losses and temporary network failures also influence our measurement technique. So to conclude, the absence of source address validation at the network edge may lead to important security issues. So there is a need for identifying networks that do not comply with BCP38. In this paper, we have presented a novel method for inferring the source address validation deployment for inbound traffic and discussed the results of the first internet-wide IPv4 measurement study. We have obtained significantly more tests than other methods and found over 49% of ASs and 23% of the longest matching prefixes vulnerable to inbound IP spoofing. We do not publicly reveal the source address validation policies, but results for individual networks can be found on our project website. We have already performed scans for both IPv4 and IPv6 address spaces and plan further scans from different vantage points. Finally, we plan to notify all operators of vulnerable networks and perform longitudinal measurements of the vulnerability. Thank you very much for your attention.